Welcome. In this topic, we're going to analyze how efficient our algorithms are so that we can compare them and choose the fastest one in each case. So first, we need to differentiate between problems, algorithms, and programs. Problems as are issues we have and we want to solve. And for example, we can use sorting as an example. We can have an unsorted array and we want to sort it. And for example, we've used the method sort a few times, but we don't know which algorithm is implemented in sort. So we have many different algorithms. For example, we have quick sort, which is so quick it finished before I showed this picture. We also have shell sort, which is a bit less efficient, and then we have the very slow insertion sort. For the same algorithm, we can of course implement it in different languages in slightly different ways, and that can also have an effect on the resulting efficiency of the program. So what do we mean by cost or by complexity? How do we measure this complexity? As we'll see, we can measure it either theoretically by reasoning about the program we've written and with mathematical equations, or experimentally by timing the amount of time we spend when we run it. We can also differentiate in terms of size. For example, this is much easier to sort than a 10,000 item array. And on what? So we do not only measure the complexity of a program, but we can also measure the complexity of an algorithm and even of a general problem. So there are two dimensions associated with these problems. The first one is the size, and the second one are the instances. So for example, in this animation here to the left, you can see that there are two algorithms, insertion sort and selection sort. Insertion sort is very fast when the array is already pre-sorted, but it's a bit slower when we're using random values. And it's even slower when the values themselves are reversed. But for example, in comparison, selection sort works at exactly the same speed in all three cases, but at a much slower speed than even the reversed version of the insertion sort, as we can see here. So when we sort a list that is already sorted in ascending order, this would give us a list such as 1, 2, 3, up until 99. And this will give us a list from, this was from 0. From 99 down to 0. 1, 0, right? And this would be much faster to sort with insertion sort, but selection sort wouldn't care about either of this. And regarding the size, we can clearly see that if we are to sort a really sort array, so from 0 to 4, this would be much faster than if we do so for an array from 0 to 999. There are three main measurements we can take. The first one is the time cost. It's related to how long it takes something to execute. Depending on the algorithm, we can of course take advantage of computing between parallel cores, and we can distinguish many different time costs given any computer. But the main idea here is that we want to measure how many seconds something takes. There are some problems that if you run them unoptimized, they can take millions of years to run. And if you optimize them a bit, they can be solved in just a few minutes. We also have the space cost, and this relates to the amount of memory that our program executes. For example, we've already seen that it's much easier to run through a list like this if we run with a pointer than if we produce slices and remove elements from them, because we will use more memory in this case than in this one. Of course, if you exceed your computer's memory capacity, the program will crash and you will not be able to compute the result you wanted. And finally, there are other measurements and other constraints when we compute things, such as the energy cost, which can be divided into the direct cost, so the energy directly required by the computer or the smartphone or whatever, and the indirect cost. So, for example, the cooling of the computer will also be a cost. And for an example, if you have apps that run on phones and watches, they are very energy constrained. So you have to be very careful about the operations you perform. The energy cost is very closely related to the time cost, as every second that you run the processor at full speed, you'll be consuming a certain amount of energy. In general, when we talk about the cost of an algorithm, we talk about the cost of that specific algorithm, and we do not care about the specific implementation. So we can measure the time that a program takes, right? A specific implementation, a specific sorting.py, for example. We can say how long that takes to run, but we can also talk about the cost of a specific algorithm, and then we can talk about that algorithm in the abstract, absent any specific implementation. And finally, we can also think about the cost of a specific problem, and that would be the lowest cost of the fastest algorithm that solves it. And for example, for a few problems like factorization of primes, there are new algorithms coming up with quantum computers that lower the cost every day.